In this chapter, we're going to be focused specifically on slope and the rate of change. In this lesson, we're going to look at the Pythagorean theorem and the tangent ratio, but with the understanding that it's related to slope. Okay, hi everybody. So in this lesson, we're going to take a look at the Pythagorean theorem and the tangent ratio. Now, I know in this chapter that might seem a little out of place because we were just talking about fractions and ratios, percentages, proportions, and so on. Now all of a sudden we seem to be going towards trigonometry. Okay, the Pythagorean theorem and the tangent ratio here. But there's a good reason for that. Okay, and you should see the connection coming up here shortly. So just quickly to review the Pythagorean theorem, remember that if you've got a right angle triangle, okay, probably we should put a right angle there. If you take the length here, form a square out of it, take the length here, the length of the leg, and form a square out of it. When you take those two areas together, that sum is going to be the same as the area formed with using the hypotenuse as the side. Okay, so we see here that the hypotenuse area is equal to the sum of the two leg areas. Okay, we write it like this. Or sometimes you'll see it written like this. I mean, a lot of people say a squared plus b squared equals c squared. Now, that's the default, but that only really works if you've labeled it that way. If you've made this a, you've made this b, and you've made this c. Okay, if you switch the letters around, then that doesn't really work. Now, there are three problems you can use the Pythagorean theorem for. Okay, you can, one, test to see if an angle is a right angle triangle. Okay, or a right angle, I should say. Just plug that in. Plug in square the two legs, add them together. If you get the square of the hypotenuse, then it's a right angle. If the value that you're getting is smaller than you think, if the hypotenuse, that you're getting here is larger than the number that you're given, well, then that's an acute angle. If it's smaller than the side that you're given, well, then that's an obtuse angle that you're looking at. Okay? Now, you can find the measure of the hypotenuse given the two legs. So, I mean, and we've done questions like that before. Or you can find the measures of one of the legs given the hypotenuse and one of the leg here. So these are the two traditional ways of doing it. The first one here requires just a little bit more insight into what's going on. Okay? So just to give you an idea here, let's say that you're checking a triangle. It looks something like this. You're not sure. Here's your A, here's your B, here's your C. This angle right here is not a right angle. If I was to take a squared plus b squared, it would be anticipating a longer side here. So if the actual side that I'm given is smaller than the one that I calculate, that's because that's an acute angle. And then the opposite would be true if this was an obtuse angle. Anyway, let's take a quick look at a couple of examples before we move on. Okay, so for this triangle right here, or this question I should say, for each diagram determine the measure of the unknown side or length or angle to the nearest tenth of a unit here. Now, actually when it talks about determining the angle, what we're really going to do right now is just determine whether it's right, acute, or obtuse. So let's take a look at this first example here. This is the angle theta that's of interest to us. Right now we're just going to test to see if that's right, acute, or obtuse. So we're going to use the Pythagorean theorem here. We're going to check this out here. So 11 squared plus 9 squared, is that equal to 15 squared? I'm going to put a little question mark over top because I don't know that that's actually equal. I'm guessing that it is. Well, 11 squared is going to be 121. 9 squared is 81. Okay, and 15 squared is going to be 225. Now, when I add those together, 121 plus 81, I get 202. Okay. So if I take, this might even be clear, like right now this number is smaller than the one that I'm getting here. If I take the square root of 202, this might help make it even clearer here. The square root of 202 is right here, suggesting that, here, we'll do it like this. The square root of 202 here, whoops, can't see it, is approximately 14. So to be a right angle triangle, this side here would have to be 14. So I'm expecting a side that's a little smaller. This one's actually bigger. So this isn't a right angle. Okay, this is actually obtuse. Okay, so theta here is obtuse. This line is actually longer than it's supposed to be for a right angle triangle. And that's what we're talking about up there. Okay, So those aren't the same here. Now over here, let's use the Pythagorean theorem to find the missing side. In this case here, that's going to be side A. Remember how we label triangles. If that's capital A up there, the opposite side of the triangle is going to be little a. Okay, so we're going to get a squared plus 13 squared is equal to 20 squared. Okay, that's just, remember that's how that works here when we plug those values in. So 13 squared, whoops, sorry, I don't want to do that quite yet. 13 squared, so this will be a squared plus 169 is equal to 400. Okay, and so now I will go 20 squared minus 169, because I have to bring that over here, so I'll get a squared is equal to 231. And remember that to finish that, I simply need to take the square root. And so the square root of that answer right there is roughly 15.2. A little dot there, 15.2. That's what we wanted, to the nearest tenth of a unit here. Okay, and that's those are a couple of examples of how we might use the Pythagorean theorem. All right, now let's take a little bit closer of a look here. Well, let's just zoom that in a little bit, or focus that. Recall that the tangent ratio involves the opposite and the adjacent side of a right angle triangle. So we focus on an angle here, and that helps us identify opposite and adjacent sides here. And the tangent ratio puts those two together. So the tangent of angle C is going to be the length of the side opposite angle C compared to the length of the side adjacent. So, and this is really, you know, the trig functions here, they are ratios. So this is why they do really fit in this chapter as well, in a chapter where we're talking about ratios and proportions and whatnot. So in this diagram, the measure of angle C, down here, can be found using, remember, the inverse of the tangent function. So on your calculator, what you do is you would simply press your second tangent button to access that function that's up there above that tangent button. And that's what helps you go backwards from a ratio to an angle. And that's it. So this is just review. I mean, we've seen this before. So let's take a look at a really quick look at a couple of examples here. So this question reads, for each diagram, determine the measure of the indicated angle to the nearest degree. Okay, so here's our angle right there, our theta right there. And this is that question that we were looking at just a few moments ago. Now we're going to figure out exactly what that angle is. So for this angle right here, the side opposite it is 9, and the side adjacent to it is going to be 11. So the tangent of theta is going to be 9 over 11. So I have the ratio, so to get that angle, I will enter the inverse tangent of 9 divided by 11. So we go to the calculator, second tangent, to access that inverse tangent function. 9 divided by 11, and this is going to take that ratio of sides and convert it into an angle. So to the nearest degree, that was 39 degrees. In this triangle right here, again, here's the triangle, the angle that's significant to us. This is the one we want. The opposite side is 320. The adjacent side is 85. So the tangent of angle P is going to equal 320 divided by 85. Now again, I want the angle, so what I need to do is the inverse tangent function of 320 divided by 85. And again, that is just calculator work. So second tangent, 320 divided by 85. And we get approximately 75 degrees. There it is. It's as easy as that. Okay, so now let's take a quick look at kind of the overlap of these ideas right here. So in triangle ABC below, the slope of the line segment AC, okay, which is going to be the ratio of the rise to the run, okay, which is going to be the length of side C over the length of side A. Now I want you to think about that. The rise is going to be side C over A, rise over run. The tangent of angle C is going to be the length of the opposite side over the adjacent side. It's going to be C over A as well. Okay, so that's one of the reasons why this is an important overlap. And this is why we can look at at a little bit of trigonometry, or specifically tangent, when we're working with slope, because they end up being basically the same thing. The slope of line segment AC, the hypotenuse, is the same as the tangent ratio of angle C at the base there. Okay, so it's a really important point here. It's an important connection to make as well. So remember that the tangent ratio is the fraction or decimal we use to calculate the angle, but it is not the actual angle measured in degrees. Now that's important. Very easy for people to just get confused between the ratio and the angle. In order to get the angle, remember you have to use the inverse tangent. The angle is the inverse tangent of C over A, and now we can even be more specific. It's going to be the inverse tangent of the slope. Okay, and actually, that's an important connection there, because the angle that we find is then called the angle of elevation from the horizontal up. Okay, that's what we call that angle of elevation. So here, from the horizontal looking up along that line there. So anytime you measure an angle, again, from the horizontal up, that is called the angle of elevation. So now, we're going to take a couple minutes. We're going to do some questions where we put all of that together. Right. So now we're going to use those skills, putting them all together here. So here's our question. A roadway rises 3 feet from the street to the garage, which is a horizontal distance of 12.8 feet. So how long is the roadway? Okay, well, that's asking us for the hypotenuse, and it helps to really draw this one out here. So, again, a roadway rises 3 feet. Okay, remember that little apostrophe there means feet here. For a horizontal run of 12.8 feet. Okay, so I can either use FT or I can use the little mark there. So I'm looking for the hypotenuse. So I know that 3 squared plus 12.8 squared should equal my hypotenuse squared. And now I pull out the calculator. So 3 squared plus 12.8 squared gets me 172.8. But remember, that 172.84, that is my x squared. That's my hypotenuse squared. So the next thing I need to do is take the square root of that. And I get 13.1. Okay, roughly 13.1 feet. That's the length of that roadway. Now, let's go over here. What's the slope of the roadway? Well, slope is going to be rise over run, so that's going to be 3 feet over 12.8 feet. Now, just like we were talking about earlier in this chapter, this is a ratio. I need the units to be the same in order for that to really communicate something important. Okay, but they are the same. 3 feet, 12.8 feet, that's good. That really doesn't help me out, though. So what I might do with that to make that number mean a little bit more to me is I might actually divide that out and get that my slope here is roughly 0.23. Okay, roughly. Or, if I convert that, 23%. And that actually might communicate a little bit more to me than this number over here. The 0.23 is pretty good, though. 0.23, you might think it rises, like, let's say, this is out of a percentage here, it's like 23 feet over 100, but it's a little less than a quarter. And that's probably even a more significant way to think about it. Now, what's the angle of elevation of the roadway? Well, the nice thing about that is we know that the angle of elevation, let's call that theta, is the inverse tangent, and I did that up above there, of the slope. So in this case, it's going to be the inverse tangent of that 3, divided by 12.8. Now, I could have used this up here, but, I mean, I've got the numbers already. There's really no reason to throw in that rounded value. So let's go to my calculator. The inverse tangent of 3 divided by 12.8. And we get 13, roughly 13 degrees. That's probably, in terms of answering this question, or at least getting a sense of what's going on with this roadway, or this roadway here. Okay, that's probably the best way of interpreting it, because I think everybody has a relatively good idea of what 13 degrees is. Okay, it's pretty small. Let's take a look at this next question here. A 15-meter long ramp covers a horizontal distance of 13.5 meters. Okay, let's draw that out. So the ramp itself is 15 meters long, and horizontally it goes over 13.5 meters. So the question is, how high up does it go? Well, that's, again, if I've given you two sides of a right-angled triangle, this is a Pythagorean Theorem problem. So it will be 13.5 squared plus x squared will give us 15 squared. Okay, so I'm going to find those numbers here. 13.5 squared. Oops. It's going to be 182.25 plus x squared equals 15 squared is going to be 225. Now, I'm going to subtract that 182.25. I'm going to subtract that from both sides. Okay? And bring that over so I get the x by itself, or the x squared, I should say. So 225 minus the 182.25. So 42.75. Now remember, that's not a final answer until I take the square root. So I take the square root of that answer, and I get roughly 6.5 meters is how high up that ramp is going to come. So from there, I can answer, what is the slope of the ramp? Well, the slope of the ramp is going to be that rise, 6.5, and it's just going to be approximate, because this is an approximate value here, over 13.5. Don't really know whether that's really communicates something nice to me. I mean, I can tell that it's going up a little bit less than half of how far it's going over, but let's figure that out here. Let's use the number that we had in here. I'm going to put this as a decimal. I'm going to divide that by 13.5 to get this 0.48. Okay, so this is roughly 0.48 or 48%. Okay? So in other words, 48 over 100. And that might communicate a little bit more to me. However, when it comes to this ramp here, it's probably going to be this last one here, this angle of elevation that communicates the most. This is going to be the inverse tangent of that slope there. So my theta here is going to be the inverse tangent. Whoops. Inverse tangent of, and then here's my slope right here. I had just figured that out. So I'm just going to go back up there, grab that. Puts it to several decimal places, and I think there's even a few more in its memory that's not showing. And there we go. 25.8 degrees, roughly. And that probably communicates, in terms of this ramp here, that probably communicates the information the clearest to me. Just like in that last question, that 13 degrees probably gives it to you in the most clear manner. So now in this lesson, what we want to do is we want to take a look at working with the grade of a roadway. Now I've hinted at this, I've suggested this with a couple of the problems we've looked at before. Now we want to look very specifically at it. So the slope of a roadway is commonly called the grade of the roadway, and it's usually represented as a percentage, just like I'd suggested before here. So the steeper the roadway, the greater the percent of the grade here. So percent grade is rise over run, slope, multiplied by 100. So that's all we're doing. We're converting the slope into a percentage here. So the problem could ask for the percent grade, it could ask for the rise or the run of the angle of elevation, depending on the information given. So we're hoping that we've given you enough tools that you can take this bit right here, considering the fact that this is a ratio here, you should be able to do multiple different things with it. Now, let's take a look at some questions here and see if we can make sense of it. All right, so this question says, one stretch of highway in the Rocky Mountains has warning signs that advertise a percent grade as 11.5%. Now, we're going to express this as a slope. So what we want to do here, remember, a slope is rise over run. It's expressed as a fraction. So our slope, what we're going to do, if we know that the percent grade is 11.5%, what we're going to do is we're going to convert that into a fraction. So that is a 11.5 over 100. Now, that's not the best way to do that, to express a fraction here with a decimal in it. So one thing that we could do here is we could multiply the numerator and the denominator by 10. And if we multiply numerator and denominator by 10, we get 115 over 100. And then one of the things we can do here is we could divide 115 and 100, sorry, over 1,000. My mistake. Okay. I can't believe I did that. Shoot. Sorry. You have to multiply numerator and denominator by the 10 in order for that to work. Okay. So anyways, once you do that, you can divide numerator and denominator here by 5 because they're both divisible by 5. And we get 23 over 200. Or, because we'd looked at this before, you could simply take and move the decimal 2 places over and simply write your slope as a complete decimal, as 0.115. Okay? Either way here. So I take the percentage and I simply write it over 100. There's my rise over my run. All I did here was just pretty it up a little bit. Multiply by 10, but you got to do that to numerator and denominator. Then I simplified by dividing out the 5. That 23 over 100, though, is those numbers are awkward. I don't have a clear image of them in my head, so maybe the writing it as a decimal is a little bit better. Now, let's calculate the angle of elevation. That's going to be theta here, and we know that that will be the inverse tangent of the slope, which in this case will be the inverse tangent of 0.115. And I can do that in this case here primarily because that's a terminating decimal. Okay, so it's easy enough to just write that out there in its entirety. So this will be the inverse tangent of 0.115. Okay, and we get to the nearest tenth. Let's make that 6.6 degrees. Okay, that's pretty shallow. It's pretty low here. Now, what is the rise of a 200-meter run of this highway? Okay, well, in this case here, you know what? I might actually go back and use this, what I just figured out here. Because that's a nice little expression for rise over run, so 23 over 200. And now I'm going to set up a proportion here with that slope. I want to know what the rise is, I don't know, over a run of 20 meters. So I know what the slope is, and then I'm given one other bit of information here, so I can set up this proportion. And now I'm going to cross multiply, so I'm going to have 23 times 20. Whoops, just doing that on my calculator here. So 23 times 20 will be 460, is going to equal 200 multiplied by x. And then I'm going to divide that 460 by 200. And I'm going to get 2.3 meters is equal to x. Okay, when I divide that 460 by that 200. And so there you go. So there's a few things that you can do with that initial bit of information about the grade. Now let's take a look at another question. Okay. In order for water to run away from a house, the ground should slope downward about 3.5 inches for every 12 feet of run. So calculate the slope of the ground here. Okay. So the slope is going to be the rise over run here. Now this is interesting. We haven't really done a question like this before. The ground should slope downward. Okay. Okay. Well, that means we need to lose 3.5 inches for every 12 feet of run. Okay. Now, there is a problem here. There is a problem because this is in inches and this is in feet. So I need the units to be the same, okay, in order to make this comparison. If I simply put a 12 down here, that's incorrect. That's going to give me a very confusing answer here, and then I wouldn't be able to convert it to the percentage grade properly because the units are wrong. So the ratio that I'm creating here is incorrect. But what I know is that there are 12 inches in every foot. So if I take that 12 feet and multiply that by 12 inches per foot, that's going to get me 144 inches. So this is actually going to be negative 3.5 inches over 144 inches. Now, I wouldn't really worry so much about the negative. The negative is simply suggesting here that it's going down, okay? That it's not rising. I mean, it's the other way you could look at it, you could just flip your perspective around and think this is rising up to the house or it's dropping down away from the house. It doesn't really matter here. Now, I don't know. I don't particularly like that little that decimal in there. So I'm going to multiply top and bottom by 10, just like I did before, but this time I'm going to do it correctly. So negative 35 over 1,440. And then maybe what I'll do is I will take and divide both of those by 5. And if I do, I'm going to get negative 7 over 288. And I'm pretty sure that that doesn't go any simpler than that. So that right there is the slope of the ground. I drop 7 inches for every 288 inches I go across here. So that's pretty small. If I want to get this into a percent grade, remember that what I do here, this is going to equal the slope multiplied by 100. Okay, so now what I'm going to do here is I'm going to take that 7 over 288. And notice in this case here, I don't even really care so much about the negative. The negative was just giving me a direction that it was going. And again, like I said, if you simply switch your perspective on that, you can see it as going up as opposed to going down. So it really wasn't an issue here. So 7 divided by 288, let's multiply that by 100. So slope multiplied by 100 is my percent grade. So to the nearest tenth, that is going to be 2.4%. That is not very much. You don't need much of a grade for the water to effectively run away from the house. Good. Okay, one other application that we want to look at here is when we're working with the pitch of a rooftop. Okay, and I mean this really affects everybody here. Okay, I mean you're probably living someplace where there's a bit of an incline to your roof, so that the water will drain away there. Okay, and that's what we're talking about here. So the pitch of the roof is the same as the slope. So this means that a roof with a pitch of 8 to 5 has a rise of 5. Sorry. Wow, has a rise of 8 and a run of 5, or a slope of 8/5. So that's what that means here. Now, oftentimes you would hear them talking about the pitch of a roof in terms of that ratio there. So working with pitch is basically the same as working with slope. Just remember that pitch is equal to rise to run. So if you were asked for the pitch, you could be asked for the pitch, the rise, or the run. So we basically could ask you for any part of that. We'd give you 2 of those pieces and ask you for the third. Or the other thing I need you to think about here is it's important to understand that the width of the building or the width of the rafter after the span of the roof is not the same as the run. Okay? So what we want to show you here is just width or span versus run here. So this is the width of the house. But that's not the run of the rafter. It doesn't go from here to here. That would suggest that the graph goes up all the way. It doesn't. It's only going to be about half of it. The run of the rafter is basically just half of that distance. It's from the edge just to the center there, or to where that peak is. Because quite honestly, it could differ on both sides depending on the shape of that roof there. Okay? So remember that the width or span is usually double what the run is that you would use to find the pitch of the roof. So therefore, if a question gives you the width of the roof or house, you need to divide that number by 2, typically, again, to get the run. All right, let's take a look at some questions. Okay, let's take a look at the questions here. So the roof of a shed has a 310 pitch. If the shed is 12 feet wide, what is the rise of the shed? Okay, so the roof of a shed has this 310 pitch here. Okay, so what we're thinking here, we've got our shed right here. It's going to goes up, down here. So if the shed is 12 feet wide, okay, remember this is 12 feet wide. That means the run, okay, the run here is going to be 6 feet. So what's the rise of that shed? And actually, it should really be the roof of the shed is what we're asking for. What's the rise of the roof of the shed? So we don't know what that is. So 310 pitch means rise over run. And in this case, I don't know what the rise is, but I do know that the run is going to end up being 6 feet. Okay? So we will cross multiply. So 3 times 6 is going to be 18. 10 times x is going to be 10x. I like that. And then to get my x here, I simply have to divide by 10. And dividing 18 by 10 is just a matter of moving the decimal over. So this becomes 1.8 feet. is x. So that's the rise of that roof on the shed. Okay, let's take a look at this other one here. What is the pitch of a roof on an A-frame building if the rafter is 4.5 meters high, and the rafter height is 4.5 meters and the rafter width is 8.5 meters. So again, the issue here is we're trying to get you to think this one through here. If the width is 8.5 meters, well, that's all the way across here. So in order for me to find the pitch, and remember with the pitch I'm trying to find slope. It's basically slope here. I know that the rafter goes up 4.5 meters. But if I take 8.5 and divide it by 2, I'm going to get 4.25 meters. And that's really what I want here. So I want this to be my run. So my rise, 4.5 meters over 4.25 meters. Okay? Now, to get that into a pitch, normally we would want to clean that up a little bit. Okay, make those numbers that are easier to work with. Now, I'm pretty lazy. I just like moving the decimals over. I'm going to multiply numerator and denominator by 100 so that I can move the denominator 2 over. So this would be 425, and that's going to make this 450. Now, both of those numbers are going to be divisible by a really nice number, 25. Okay, and so that's going to be 18 over 17. And so that becomes my pitch, 18/17. Okay, that would be the pitch of that A-frame building there. Now I just want to double check this as well here. So what is the pitch of a roof on an A-frame building? 4.5 meters and 8.5. Yeah, those are relatively close to one another. So that's why the slope is quite low. Now, last question here. The rafters of a shed are asymmetrical, with one side having a pitch of 410 and another one having a 4 to 6 pitch. What is the roof? What is the roof? Oh boy. What is the width of the rafter if the height is 3 feet? Okay, now that's a good question here. So what we're going to have here is, here's our rafter here. The pitch is smaller on one side than it is for the other here. So 4 to 10, remember this is rise over run, rise over run. As soon as the run gets larger here, that's not quite as steep. Okay, so this right here, this part of the rafter is going to have that slope of 4/10. This one here is going to have that slope of 4/6. And if you compare those two numbers, this number is larger than this one. When the denominator gets larger, the value gets smaller. Okay, so this goes up 3 feet here. So what I want to do here is I want to figure out what this length is and what this length is and add them together. So my total will be x plus y. Now, I need to figure out what that missing piece is. So in both cases here, it's the run that's missing. So on the left-hand side, I've got a slope of 4 over 10, rise over run. So my rise is 3, my run is x. Cross multiply, so I'll get 4x is equal to 30. Okay, and if we divide 30 by 4, we get 7.5. Okay, so 7.5 feet. So there's my x. So right there, I can go back and write that as 7.5 feet. And we're going to add that to this one right here. Well, we know the slope of this line is 4 over 6, rise over run. I know the rise is 3. It's the run that I don't know. I'm going to cross multiply, so 4y is going to equal 18, 6 times 3. And then when I divide here, I'm going to get 4.5 feet. So 4.5 feet. And when you add those together, we get 12 feet total across the width of that rafter. Anyway, so that was basically, this is the sort of question I was talking about up here when I said that usually we simply divide them in half. But we don't have to. Okay, depending on the shape that you want, you can have these asymmetrical rafters.